Vanakkam. Welcome to this course on biomedical instrumentation. We started looking at the visual system, specifically with an interest to look at the ERG or the electroretinogram, and later we will look at also the electrooculogram. In this video, we will look at ERG electrodes or electroretinogram electrodes, and what is the electrophysiology of the eye and the spatial properties, what are the various types of ERG, signal characteristics and types of ERG signals, and equipment for electrodiagnostic testing of the eye, stimulators and what are called as the revolutionary Ganzfeld stimulators. ERG essentially is the process of recording the potentials generated by the retina in response to light stimulation. Essentially there is a measurable voltage or potential that exists between the cornea and retina. What is the source of this? This is due to the retinal pigment epithelium. This retinal pigment epithelium essentially maintains a trans epithelial potential, and this is the foundational reason as to why there is a potential difference between the cornea and the retina. So, this essentially varies with light intensity and the duration of light, and ERG signals are generated using a corneal electrode, and this corneal electrode is placed on the cornea using a contact lens. So, there is a contact lens within which the electrode is placed, and then it is placed on the cornea, and a reference electrode is kept on the skin near the eye or the forehead. Typical amplitudes of ERG are around 500 microvolts, and recordings are made using typical biomedical amplifying analog front ends and recorders. So, essentially you record ERG using silver chloride electrode. Why is that? Because minimal polarization. What is the half cell potential of silver chloride electrode? Long time ago we did discuss this, about 222 millivolts. Half cell potential of silver chloride electrode, so which is an excellent minimally polarizable, and we can also use it in small sizes such that it can be embedded in a saline filled contact lens. That means that it can maintain good contact with the cornea, and essentially helps to provide readings for a relatively long time. See, essentially the eye is a fluid filled sphere, the retina is the thin electric source that is acting at the posterior pole on the back side of the cornea, behind the cornea, and this is where the electrodes are placed. This is the electrode that is placed on the cornea, and the reference electrode is either placed here or placed here above the eye on the forehead. And unlike EEG and EMG, which do not have any specific form, and similar to ECG, which has a specific form, recall ECG has this typical PQRST wave. Similar to that, ERG waveform has specific components, like you have an A wave, you have a B wave, like you have the PQRST wave in ECG, you have the ABCD wave in ERG. There is an early receptor potential, which is essentially the immediate or the instantaneous response from the photopigment changes. As soon as the light is there, there is an immediate response that you see, which is the early receptor potential, and this is essentially proportional to the light intensity. That is what you are seeing here. It is the early receptor potential. Then you have the A wave. Then you have the A wave, which is the initial negative deflection in the ERG, which is due to photoreceptor hyperpolarization. Recall that intensity of light essentially hyperpolarizes, and then the bipolar cells produce the action potentials at various frequencies. This is the physiology we discussed, very brief physiology. So, that initial negative deflection is reflective, excuse the pun, the initial negative deflection is essentially representative of the photoreceptor activity, hyperpolarization that happens at when light is incident on the cornea. Then from the inner retinal layers, you have the activation that starts, which is the bipolar and the ganglion cell activation that happens, that is there, that is the B wave. Its amplitude is compromised in case of diseases, or it is absent if inner retinal function is severely compromised. So, by reading this ERG, you can come to a conclusion of which part of the eye is having the disease. So, excellent diagnostic tool. Then you have C wave, which is essentially reflective of the RPE activity. Recall what is RPE? RPE is retinal pigment epithelium activity. This is generated by the layer that is embedding various photoreceptor segments, right. This essentially follows the early receptor potential, the A wave and the B wave. Following this is the D wave, which essentially represents the off response in ERG, that is that wave, this is D wave. This happens when the light stimulus is turned off, reflecting the bipolar activity, bipolar cell activity during the off state. Now, different components or changes in different components of this ABCD ERG essentially is reflective of different diseases. What are these? For example, compromised reduced A wave might mean that it is due to some photoreceptor problem, right. It is due to perhaps due to some photoreceptor disease such as retinitis pigmentosa. Now, if the B wave is compromised, let us see, reduced B wave, what does it signify? This essentially says that if the A wave is intact and the B wave is compromised, this means that there is an inner retinal dysfunction or congenital inner retinal disease or congenital stationary night blindness or CSNB. This is the other problem that could be causing a reduction in the B wave. What else could be that? Or it could be due to retinoschisis. Okay. A negative ERG could be due to retinoschisis or due to various such challenges, various such diseases, or maybe due to CSNB. If the ERG itself is absent, that means that there is a total retinal detachment that has possibly happened. Okay. So, these are the various ways in which I could diagnose what is what. Also, you can record ERGs from localized regions of retina, not just the entire retina. So, essentially full field ERG is the sigma local ERG due to linear superposition. This has been confirmed in humans and frogs. Critically, it is important to prevent scattered light from unintentionally stimulating larger retinal region areas. Now that is a critical, which means that you need to have a stimulator that prevents other scattered light from from presenting. So, you need to have a specific light source that provides only the light stimulus of interest. So, you need to have that care. We will look at that in future slides as to what this is, a specific stimulator type. So, essentially you need to have a high background plus a low intensity stimulus that reduces sensitivity to scattered light and provides a low amplitude and localized ERG that then requires averaging across multiple responses. But then targeting specific regions within the retina is quite challenging because of optical and anatomical limitations. You cannot place the electrode wherever you want, and despite these challenges, localized ERG is critical for assessing the retinal function and retinal behavior. So, essentially ERG is provides an objective measure of the retinal activity by making measurements that are independent of optic nerve or the neuronal pathways and are actually quite minimally affected by the optical properties or the media opacities such as cataracts, for example. Something to keep in mind. So, there is an objective measurement of the electrical activity level of the retina, that is what is provided, without getting much affected by, for example, the presence of a cataract. There are different types of ERG. Full field ERG, which is essentially it uses brief light flashes over the entire retina and measures the response from the entire retina. This is used to detect the overall retinal diseases like retinitis pigmentosa. Whereas pattern ERG uses repeating patterns like checkerboards. We will discuss this very briefly. I said we will not discuss it, but we will discuss this very briefly. And it essentially measures signals from central retina and optic nerve or cells of the optic nerve and helps detect problems like early glaucoma and optic nerve damage. Multifocal ERG represents multiple small light spots that are incident on different areas or regions and records responses from many small parts of the retina at once, and then you can use them for summing. This is useful for finding macular disease of the macula and identifying any localized damage. Note that overall ERG signal amplitude ranges from about half microvolt to about 1 millivolt, and the oscillatory potentials are between 0.1 to 100 microvolts, and the frequencies are in the range of 100 to 300 hertz and can be generated from other ERG signals using band pass filters. These are the oscillatory potentials. Pattern ERG has lowest signal range of between 0.1 and 10 microvolts and requires the highest amount of amplification. But then if you have high amplification, it will also increase noise. So, which is why it is important to average across multiple recordings to make sure that the signal to noise ratio is at an acceptable level. And the signal frequency of A and B waves is between 0.2 and 100 hertz. So, this is evoked by alternating checkerboard stimulus and reflects the activation level of the retinal ganglion cells. And then you have the flash ERG. There are different adaptation and components. To the dark adapted eye, the response is primarily from the rod system, and the light adapted eye, the response is primarily from the cone system. A wave essentially is the initial negative deflection, and the leading edge is produced by the photoreceptors. We saw this, and the remainder is produced by the a combination of photoreceptors, amacrine cells, bipolar cells, Muller cells and Muller glia, which are essentially glial cells. And then B wave is a positive reflection that is due to the activation, actually an activation of ganglion cells, but perhaps also including several cells including photoreceptors, bipolar, amacrine, Muller cells or Muller glia. So, for performing the electrodiagnostic testing in the eye, it requires two main components, a stimulator and a recorder. You need to find out, you need to stimulate with a specific light, and equipment used for pattern ERG, EOG and visual evoked potential is often similar. They are quite, they are not different from each other, but some of them can perform all of these tests simultaneously. Usually you have what are these called as Ganzfeld simulators. This is a hand drawn image in PowerPoint, I think, drawn by my teaching assistant, hand drawn image, and it says fitters, it is not fitters, rather filters. Okay. So, there is a Ganzfeld stimulator that is going to provide the light source, and then there is a recording from the silver chloride electrode, and then there are amplifiers and filter banks that then converts this data into digital form using the analog to digital converter, and there is a controller that changes, and then there is a display through which the physician can check the required information, required image. The stimulators present a crucial aspect of the ERG testing. They provide controlled light source. I already mentioned this. You need to prevent scattered light from that. So, they can produce specific spots and patterns, and they can vary intensity, color, size and frequency. That they also allow the ability to change the patterns or background intensity and color, and they are usually controlled in sync with the recorder. So, you know what is it, whose response, your you know response to which particular stimulus are you recording. So, they are usually synced with the recorder. They are usually known as the Ganzfeld stimulator, Ganzfeld bowl or the pattern stimulators. Required stimulation is typically projected on a white surface or produced by an LCD screen. It is critical to keep calibrating this equipment from time to time. The amplifiers, what is the main purpose? Essentially to amplify, to magnify these signals that you get from these electrodes, which are the order of 1 millivolts or slightly less than 1 millivolt. Gains are from 1000 to 10,000, and input impedance is typically of the order of 10 megaohms. Right. CMRR should be very high, about 100 dB at 50 or 60 hertz, to avoid the common mode noise, which is the electrical noise, and you can have AC coupling to avoid distortion from small DC voltage differences. Some systems allow DC to prevent the lockup of the AC, and each of the amplifier stages gain, there are different, the amplifier has multiple stages, must be linear within its input range. That it must have very low noise characteristics of the order of 1 microvolts in RMS. Filtering is performed after first stage amplification to ensure that noise is minimized before further amplification, otherwise noise will also get amplified. Right. It can be analog or digital signal processor based filtering. So, you need low pass filter, you need band pass filter, and you need high pass filter. Often we prefer Bessel filters due to better time domain characteristics. Notch filters are usually used between 50 and 60 hertz to minimize interference from common mode noise, such as the power line interference. Although there is significant signal power between 50 and 60 hertz. So, you need to have excellent filter characteristics to have an acceptable level of signal to noise ratio. There are many ways in which you could process this image, just touching upon some of them, essentially Fourier transform, 3-point smoothing, averaging, there are many such things that you could do with these. And you need to have isolation of the electrical isolation of the patient. This is achieved by driving the initial stage amplifier with batteries as opposed to power line. And output of the first stage amplifier can be connected to the next stage by using isolation methods. Typical isolation methods, we will look at some of these in future classes, what are the various isolation methods that are provided. In this case, we can use, for example, optical isolators or opto isolators unrelated to the optical system of the eye. And then you have analog to digital converters, which convert the recorded analog voltage into digital form so that it can be stored and processed in a modern computer system. So, minimum acceptable is 12 bits, preferably 16 bits is good. Nowadays, commercial systems even offer 24 bits, which is an excellent for providing resolution of up to 0.06 microvolts. And the sampling frequency usually you choose depending on the range of the system. Usually, you are interested in measuring. The commercial systems usually offer between 300 and 5 kilohertz. This is more than sufficient for all the electrophysiology signals of interest for us. And the stimulator itself provides high density, high intensity flash or light with the uniform background illumination and avoid scatter. That is the critical part. This is the Gansfeld stimulator. It is an hemisphere typically about 50 centimeter in diameter with an inner surface coated in matte paint, and the patient sits in a darkened room looking into the stimulator during the test, and the light sources are traditionally background illumination using an incandescent light bulb or light stimulus using xenon flash lamp. Nowadays using LEDs, laser LEDs. You could control the timing, color and the intensity of stimulus are all electronically controlled, and this is synced with the recording system. So, and it can also have color filters that is used to create the required background of interest. Modern systems, modern Gansfeld stimulators nowadays use LEDs for both background and the stimulus. The good thing with these kind of stimulators is that they provide self calibration for both color and intensity. There are this International Society for whatever, check what this is, ISCEV standards for clinical examination and allow design of custom tests for research purposes. So, these are the typical components of a ERG system. We saw what these are, the ERG electrodes, silver chloride electrode. What is the impedance of this electrode? Less than 5 kilo ohms. Right. The spatial properties, the types of ERG and signal characteristics and its types, and what are the various equipments that are there, amplifiers, filters and analog to digital converters, and stimulators, critically stimulators in the Gansfeld stimulator. With this, we come to the end of this video. Thank you very much for your attention.